I'm going to show you how to use Euler's method.
We use Euler's method to approximate the position of a point on a curve. Usually we can do this if you know the x ordinate. You can work out the y because you know the function. But if you don't know the function, we can use Euler's method to approximate it. And to do this, we do need to know some information. We do it when we know the differential equation or the gradient function, but it's one that we can't solve. And we also need to know a point on the curve. Before we get into Euler's method, there's a couple of things I want us to look at and have clear in our minds, and then hopefully we'll understand Euler's method that bit more clearly. First of all, it's to do with the gradient. So the gradient of a line is, how do you define it? That's a good definition. When you first came across it, you might have been told rise the vertical distance divided by the run, the horizontal distance of the triangle. Or else you might have been told how far the line goes up. If you start on the point on the line and you go across one, how far do you go up until you meet the line again? However, what I'd like us to have clear in our heads is this. So on our example here, the increase in x, or what I'm going to call the step length, is 1. The gradient, we know, is 3. So 1 times 3 is the increase in y. So here's nearly the same thing again. Underneath, I'll put the change in y, or the vertical change, is equal to the gradient times the horizontal change. Let's have a look at this. So here we've got the same line, same function. We've got a step length of 1. Gradient is 3, so 1 times 3 is 3. And the graph goes from -2 up to 1 at this point. What happens if we increase the step length? Well, now it's horizontally 2, so it goes up 2 lots of 3, from -2 up to 4. Now up to 3, the step length is 3, so we got 3 lots of the gradient, -2 up to 7. Okay. Now, happy with that, then we can look at the gradient function. So on the previous graph, the gradient was constant. But on a graph like this, here we've got a parabola, so we're talking about a quadratic. And this one is just y equals x squared plus 3. The gradient changes depending on the point that we're measuring it at. So here we've got a point A, just over 0.5. We've got the tangent to the graph drawn. We can see here what the gradient is. However, if we choose a different point on the line, say 1.4, the tangent would be significantly steeper and the gradient would be greater than 1.03. So here we can calculate the gradient of the graph. We can calculate dy by dx by multiplying the x value by 2. So here's a nice GeoGebra slide which shows us how that is. Just pause. So at this point, we've got our parabola. We've got a point on our parabola and the tangent drawn on. We can see it's the tangent is a negative gradient and it's going down. It's just over 2, isn't it? So it's going downhill, so it's about -2. So we can go down vertically down to the same point onto this dotted function. This dotted function is the gradient function. So it's dy by dx, and we know that's 2x already. And so at the point, that's about -1.7, the gradient is 2 times minus 1.7. So you can see it's just under minus 3, isn't it? Maybe minus 3.4. And that goes with the gradient of the graph that we can see. However, if we let the point move, we've got to 0 now. So here the tangent to the graph is nearly horizontal, and the gradient function has a value of 0. Just move this on a bit. Okay, so the point is that as the point moves on the graph, the gradient function will tell us exactly what the gradient of the graph is. Okay, suppose you don't know the function, but you do know the gradient function. Stick with u over dx is 2x. We can still calculate the gradient at any point on the graph. We just don't know what the graph looks like. Well, maybe for u over dx equals 2x, we do know roughly what it looks like. But we don't know what the y ordinate will be for the x value. So here we've got a couple of possibilities. The point on the graph might be here, 2, 4. Point on the graph might be here, 2, 5. Might be 2, 6. Could be anything, couldn't it? Depending on the function. But we do know what the gradient function looks like. We know the value of the gradient, how steep the tangent will be. Okay. What about Euler's method? Euler's method for approximating a point on the graph, we use it when we do know the gradient function, but we also know a point on the graph. Right. Let's look at an example. We know a point on a function. We don't know the function, we've got a point there. And we know the gradient function. It's a little bit more interesting this time. We don't know what the graph looks like. Suppose we want to know what the y ordinate is when x equals 2. Whereabouts is it going to be? Well, this we know, and we know the point, and so we can use the x and y values, substitute them into the gradient function, and we can work out the gradient at that point, minus 1. This is something to be aware of. This notation, it looks like a function of, but instead of one value, we've got the x and the y value. And it just means the gradient function at that point has a value of, and there we are, we've got it, minus 1. And there's a line with gradient of minus 1 going through our point. We don't know what the curve looks like. We know A is a point on the curve, and so that red line is the tangent to the curve at that point. Now, we can approximate our point for x equals 2 by saying where on the tangent will that be when x is 2. And we've got an approximation for it, even though we don't know what the curve is like. Now, this isn't quite Euler's method yet, but it's just showing you what we can do. However, certainly our gradient function, that's not going to give us a straight line. And so we can be pretty sure that's not exactly where the point will be. If the graph was linear, it would be, but we know it's not. The graph could look like that. We could have a convex curve, and the y value be much more than 1. We could have a concave curve and the y value be much less than 1. So how can we get a better estimate? This is where Euler's method comes in. If we, instead of taking one step of 1 in the horizontal and working out the corresponding y point on the tangent, we can take more smaller steps. And sometimes Euler's method is called the step-by-step method. So what we're going to do is we're going to take 5 steps. Each step is 0.2 and find the corresponding y values at each point. So we've got our starting point. We know the gradient at this point. But this time, our step length is 0.2. So if we're going to go along this tangent, 0.2 is our step. What is our vertical change? So we've got it there, minus 0.2. Our new y value is the previous one plus our vertical change, or our new y value is our previous y value plus step length times the gradient at that point. And there we've got it, our new y value, 1.8. We've got our coordinates of our point B. We've taken our first step. Now we're going to take our second step and find our third approximation for a point. So again, our step length is 0.2 again, so the x coordinate for our point C is going to be 0.2 more than 1.2. We can calculate the gradient at this point, or the gradient of the tangent to the curve, and so we can calculate our change in y. It's step length times the gradient. So our new y value is going to be our old y value, our previous y value, plus step length times gradient. Now we've got our new y ordinate for point C. Point C, we can plot it on the graph now. So we've taken our second step. How about finding and the step length is going to take us up to an x value of 1.6. We know the gradient at this point, and we can work out our vertical change. And so we can work out our new y value, our y ordinate for D. The new y value is the previous y value plus step length times gradient at that point. And there's our coordinates for point B, which we can now plot on our tangent. We've taken 3 steps. Now for our fourth, we've got our coordinates of D. Step length is 0.2. Gradient at that point. So if you think back to where we started at A, the gradient was minus 1. So it's going downwards more steeply now. We can use our gradient to work out our new y value, or work out the horizontal change, vertical change is step length times the gradient. And so our new y value is our previous y value plus step length times the gradient at that point. And so we've got our new point E. One more to go, one more step. So it's the same thing again. Step length is 0.2. We can work out the gradient at that point going through E. But it's got shallower, still going downhill, but relatively shallower. Work out our change in y, step length times gradient at that point, and work out our new y value. The old y value, or previous one, plus step length times gradient at that point. Until we've got our coordinates for our point F. Our first estimate, where we just took one big step, was at this point 2, 1. But we found out by taking smaller steps that it should be a more accurate estimate for our point on the curve. In fact, from 1 to 0.6, that's 40% nearly difference, isn't it? So that's Euler's method. And this is the key formula that we use, that the new y value is the previous y value. That's right, plus step length times the gradient at that point.